可以吗？可以。
把它分成3个部分，那就3个。因为就是一个就是应该是破塔材料嘛，另外就是那个赵老师这样子的那个3个破塔，然后我还问赵老师那个颗粒大小还没有问，然后另外一个就是那个可能打败，就只把分成3个。好啊，因为我爸说对的，就先分成3个，然后看怎么样的，看这样放一个答案就是3个答案，就变成 A B。对啊。这我就先弄好，再看怎么把它再把它结合起来。先弄好，最终应该是对。对啊，就是那个理论，应该说原理跟说明，贴完就好多，然后那个题目只有2个月。对啊。最长的现在最多版的，最大2个分上的最多，对，那超过2个3个那表，里面才能有那些那些。对吧？那个，啊，现在学生不喜欢看。应该到下礼拜应该就可以用好。我觉得我的好像歪了。
Okay, it's almost time. So we wait for a reporter to solve their projection problem.
所以这个是地理的。
对啊，对啊。
哦，所以有这么会考堂的，所以还可以有那个这样子的。
好。
哎，是这个是特别的。
对，就是手里的，它可以。
所以它是
线控它，直接线控摄影机。
哦，线控，我看到了。对。这样的话就完全非常的那个。
怎么转的时候不会弄下来。
这里的意思呢？
在直播啊，他这样在。
这个直接就是，我如果要让他做方式看，我要去哪里？
就是有我把它这样放在那个网面，
是在系上网面？
没有，是在直接网面。
第二OK。哦，直接进来就看到了。
然后这样。
那这个是一个。哦 ，OK。因为我记得我之前那个前2年我有这样看。看现场是最精彩的，但是有时候还是有事情在做。
对啊，然后有点现场会有点严肃。对，看直播会有点严肃，因为他会处理，还要处理。
不还好。
对啊，就还好。哎，准备开戏啊！要看吃早餐。
Good morning, ladies and gentlemen. I think it's time to start. So I would like to welcome you to join the 13th Typt Final Physics 5. So today we have 3 teams. So I would like to start the final competition from introducing our jurors. So,
my name is Wei Li from Institute of Physics Academic City.
My name is Min Chang from the Grand Catholic University.
Hi, good morning. I'm Wei Li from Gongcha University. Thank you.
My name is Jean-Lan Tsai from University. Thank you.
My name is Hong Yi Chen from National Global University.
Good morning. My name is Hao Yuo from National Global University. Thank you.
I'm from National Taiwan Global University.
Morning everyone. I'm Ivan Shi from National Global University.
My 宣布张庄进入台湾动物园的
Okay, I'm Dong Yuan-Xu. I will be the chairman of this section. And following, I would like all three teams to introduce yourself, starting from the reporter.
Good morning, professors and all competitors. We're Team Miracle from Jianguo High School. I'm the captain, Wu Zhengwei. This is Ye Zhonghan, Yang Yaoan, Zhang Yache, and Chen Yanli. Thank you.
Okay, thank you.
Hello everyone, it's a pleasure to be here today. We are Team All-Nighters from Taipei American School. And my name is Jonathan Bruce. I'm the team captain. And these are my team members, Alex Shaw Jr., David Lam, Rupert Liu, and Daniel Hill.
Team Xiaoxie, and I'm the captain Cai Guowen, and she's Wu Junting, Jing Guowen, Jiang Shanyu, and Wang Yiqing. Thank you.
Okay. Thanks to all three teams and all the jurors. So now today's final problem were picked up by the reporter themselves, which is a little bit different from the normal competition. The problem was decided by challenge. So now we already know the problem to be reporting. For the first stage, the problem to be reporting will be the number 14, dynamic hydrophobicity. And we will start from the preparation time for the reporter. Time is 5 minutes. Please start. Okay, since the reporter is already ready to give the presentation, so please start your presentation. Your time is 12 minutes.
Hi everyone, I'm the reporter Ye Zhonghan from Team Miracle, and today I'm going to report problem number 14, dynamic hydrophobicity. And here's the problem statement. When a drop of liquid impacts on the horizontally moving surface, the droplet may be reflected or not, depending on the speed of the surface. And in this problem, I want to focus on two key questions. droplet can be reflected and how the speed of the surface affects the drop. And here's the outline. First is the experiment setup. We use a motor to rotate the rotating plate in order to create a horizontal moving surface. And we use a cylinder to create our drop. And also we use high-speed camera to record the droplet's motion. And here's a visualization for some terminologies we use in our experiment. First is the impact speed, the droplet radius, and the impact radius. And I want to mention that the impact radius means the distance between the droplet's position and the center of the rotating plate. And also the plate's rotating velocity. And we can use R and omega to get the surface moving speed, which is ds. And also we have the surface tension coefficient of water and the density of water. And we define two Weber number, the normal Weber number and the tensional Weber number, which will be discussed later. And also the material of the horizontal moving plate is PVC and it's a hydrophilic material. And we can adjust the rotating speed or the distance R to adjust our surface moving speed. And here's our tools we use. We use tracker to track the motion of our droplet. And also we use Weber number. Weber number is a dimensional number and which can be thought about the relative between the fluid inertia compared to its surface tension. And it means when the Weber number gets larger and the surface tension is less important in the droplet. And if the Weber number gets smaller, the surface tension is more important. And so this is quite useful in analyzing the droplets and bubbles. So here are the drop generation. We use a cylinder needle system to generate our drops. And because we have two kinds of needles, so we can create three kinds of droplet diameter. And here the droplet over ml means we measure how many droplets can every ml to create. And we can use this and severe value to get our droplet diameter. And also we can adjust the drop initial height to adjust our impact velocity VI. And here's the observation of our phenomenon. Okay, so after our observation, we found out that we can classify our motion into three: the deposition, partial rebound, and the rebound. First is the deposition. As you can see, the drop simply spread out over the surface without reflection. The partial rebound. After the drop touches the moving surface and they separate into several different little pieces and partially spread out over the surface and partially reflected from it. And the rebound. And as you can see, after the drop touches the moving surface, it is able to keep its shape and then reflect it from the surface. So here comes our theory. We found out that we analyzed the motion before the drops start to reflect it, and we found out that every time, the moment before the drops start to reflect, it will create a special shape like this. And also we will left a line of water ahead of the droplet. So we can combine our theory. Because the surface is moving, so the air above the surface will drag by the surface and create an air boundary layer. And as the droplet goes down, the bottom water of the droplet will be taken by the surface. And this will create a special shape like this in our previous photo. And this shape will create a space between the surface and the droplet to let the air boundary in. And as the air boundary layer goes in, we will create a lift force for the droplet to rebound. So we analyze the surface speed and the rebound height of the drop. But as you can see, the plot is quite messy and chaotic, and it is lack of considerable effect. So we want to make sure that the rebound height is not has a clear correlation to the surface moving speed. So we make another experiment listing the same surface moving speed, and we can also observe the wide range of the rebound height. surface moving speed and the radius of the droplet. And let's see that in the same radius of the droplet, as the surface speed increases, the drop will go through 3 different motions: deposition, partial rebound, and rebound. And also, as the droplet gets bigger, the surface tension of the drop may not able to keep its shape, and that results in partial rebound because the droplet collapse. And finally, is our region map of the Weber number. And the x-axis is the tangential Weber number, y-axis is the normal Weber number. And the Weber number is here, so you can see if the impact speed and the radius increases, the Weber number will increases. And if they decrease, the Weber number increases. So as I just mentioned, the Weber number is larger. It means the surface tension is more important, and it's less important. So as you can see, when the higher tension Weber number, the increase of normal Weber number can change the drop motion from rebound to partial rebound, and that's because the VI and R affect the normal Weber number to increases, and as the Weber number increases, the surface tension is less important, so it will cause the drop easier to splash and cause the partial rebound. And here at the lower tangential Weber number, the drop motion remains in deposition regardless of the value of the normal Weber number, and that's because the drop doesn't have enough energy to splash, which means it has the smaller normal Weber number. We can predict that when the normal Weber number or the radius keep increasing, the motion of drop will eventually become partial rebound because the normal number gets larger, so the surface tension is not much important. And finally, you can see as the increase of the tangential Weber number, it can make the drop easier to rebound in higher normal Weber number. And that's because as the surface speed increases to our theory, the air layer's speed also increases, and this will cause a rise of lift force for the droplet easier to rebound. And finally, is our conclusion. First, the rebound height and horizontal speed of drops is nearly random due to the instability of the airflow and the turbulence. And also, second, the lower impact speed and higher surface speed and the boundary layer on the surface, and also all contribute to the droplet rebound. Therefore, for normal Weber number, the drop motion will go through 3 parts of tangential Weber number increase, and that's because as the tangential Weber number increase, it means the surface moving speed increases because the lift force increases. And also, the increase of normal Weber number can change the drop motion from rebound to partial rebound at higher tangential Weber number. And the drop motion remains in deposition regardless of the value of normal Weber number at lower tangential Weber number, because it's just like the end of the third one, because tangential Weber number is that lower, it means the lift force is lower. So it will not much easy for the droplet to rebound. And finally, we found that there will be a wide range of the normal Weber number to rebound as the tangential Weber number increases. And here's the end of my presentation. Thank you.
Okay, now following will be the time for opponent to ask short questions for 2 minutes. So please.
All right, thank you so much for your excellent report. I have a few clarification questions for you. First is, what surfaces did you use?
PVC.
All right, did you try changing the surface of the
No.
Okay. And how did you ensure a constant drop of volume? I saw that you used the surface, right? Is that on slide 7?
You mean the...
Yes, is that radius what you mean? Like when you dropped it out of the sphere, does the volume of the droplet change?
Because we measure how many drops can
make sure that your surface is flat?
Yes.
Alright, and you make sure that your drop height is constant.
Drop height is a kind of parameter because we use drop height to adjust our impact speed.
Alright, so when you were doing your recording, did you notice that the droplet seems to stretch and contract? I noticed that you said in your presentation that the drop both expands and contracts.
In here?
Yeah. Do you see a consistent shape between the trials from the contraction and the expansion of the contraction? Okay, let me rephrase my question really quickly. So when you drop the droplet, right, it will expand and then it will contract. Was it consistent?
No.
No, okay. And my last question is, do you have a quantitative theory that can predict what speed the surface needs to move at in order for the droplet to rebound?
No, we can't do that because the speed of the surface is quite, the speed of the air bubble layer is quite
unstable.
Yes.
Okay, thank you.
Okay, now will be the time for the opponent to prepare their presentation for 3 minutes.
I would like to begin my presentation.
Okay, now it's the time for the opponent to take the floor. You have maximum 4 minutes to present your presentation, and any time remaining will be added to the discussion. So please start.
Alright, today I would be proposing number 14, dynamic hydrophobicity. So the problem statement states that when a drop of liquid impacts on a horizontally moving surface, the droplet may be reflected or not depending on the speed of the surface. Investigate the interaction between a moving surface and the liquid. I believe that the important focus of this is that the surface is horizontal and that we need to analyze whether the droplet is reflected or not. The opponent's ideal structure of investigation goes from the phenomenon investigation, a theoretical model, then the experimentation, discussion, and finally a conclusion. So the pros and cons of the report. So the pros of the report is that they use a slow motion camera to examine the motion of the droplet on impact. They also examine the phenomenon by changing the velocity of the surface, which is very important. And they also consider the thin film of vapor between the liquid droplet and surface. However, I think they could improve on a few points, such as that they did not account for the static friction of the droplet on the surface, which I will talk about later. They also lacked changes in their parameters, and they had an unclear way of measuring the contact angle of the droplet, which I would like to re-clarify with the reporter later as well. They also lacked a quantitative theory, thus I can't find or they can't quantitatively give me a critical velocity in order to determine the rebound of the droplet, and they say the cause of that is because there's an unstable wind speed at the surface of the disk. And lastly is that they did not give an explanation for the splashing behavior upon impact and how that might affect the phenomenon. So I think a few points I would like to discuss is generally is the surface tension and rebounds, like why is the droplet able to rebound or repel off the surface. Second is the kinetic energy and the behavior of splashing, like why does the droplet splash and how does that relate to this phenomenon. Third is the static friction, how this might affect the slipping of the droplet, which they may or may not have examined when they were doing their own experiments. And finally is the surface tension and kinetic energy, like is the surface tension discussed before affected by the kinetic energy of the droplet. And with that, I would like to continue to my discussion. Alright, so the first thing I would like to say is that a small improvement you can make before I talk about all this is instead of using a syringe, I think you can try using a micropipette. That would show that the droplet you're using has a constant volume. So the first thing I would like to talk about is the idea of surface tension, and I would like to come into agreement with the programmer of this. I'll try to examine this in a much more simple way. So would you allow me to draw a diagram? Is that okay? Okay. So let's say this is the surface, right? And you have a droplet here. And this is your, sorry, let's say this is the droplet or liquid, right? This is this is your vapor or your air around here. Okay. You have a contact angle here, right? So you think here is the whole droplet. Yeah, I just drew half of it. Okay. Three surface tensions in this case. The first surface tension is the surface tension of the liquid solid. Second surface tension is the surface tension of the solid and vapor. And the third one, which is dependent on the contact angle, is the surface tension of your liquid and vapor. This is the intuitive understanding of how surface tension is for like not even a moving surface but a stationary surface. Like sort of. Do you think this is a good explanation of how surface tension look like?
Yes, I agree.
Okay. So, if we examine a rebound of a droplet, let's say the rebound looks like this, it's a perfectly spherical shape. Using this, we can determine the contact angle using cosine of theta equals to the surface tension of the vapor solid minus the surface tension of the solid over the surface tension of the liquid vapor. And in the case of complete rebound of a spherical shape, I believe this theta would be pi. So if this contact angle is pi, then you result in negative 1. So if you want to find a complete rebound of a particle, this basically needs to be equal to 1. Do you think that's also a way to examine a rebound?
Yes, but in our experiment, we found that when your droplet is about to rip, it won't create force of fear. So it was
that's a little harder to examine.
Yes.
But with this, I would like to talk about if there is a surface tension for the liquid solid, for the solid vapor and the liquid vapor, do you think changing the medium in which you conduct the experiment in will change the effect of your rebound?
You mean the medium of
the medium. So for example, you conducted your experiment in a room, finding that there's air in the room. Have you considered changing the medium? So perhaps putting your entire apparatus in the box and changing the medium
I agree with you, but I don't think that it will affect my experience too much because due to the problem statement, the point is the surface and the droplet.
Yeah, but I believe that the difference between the liquid surface and the solid vapor surface tension needs to be this difference needs to be more than the tension of the liquid vapor in order for a rebound. So I believe that the vapor is really important in this case because the surface tension between this will determine how hard it is for the droplet to rebound.
But I think because rebound is caused by the gap of air here. Agree? Yeah. Mostly affect the drop to splash is by the surface tension of the droplet. So I think this will obviously affect, but not that much. Let's go.
Next question I would like to get into, which I was a little bit confused, is how did you determine the contact angle of your liquid droplet with the surface?
No, we didn't depend on the contact angle.
Do you think the contact angle would have an effect?
No, because we only drop it vertically.
Okay, but as you know, when a droplet drops out of a certain type of lead due to air resistance and other factors, that will deform in shape, and it won't be a perfect spherical shape as it touches the surface, like you noted in this picture. It will sort of deform. How do you
Yeah, I agree with you, but because the air and the water, the air is deformed to the water, I think it's not that too much. We also didn't consider, and the contact angle is in the correlation between as a relation between the force magnitude. You're saying increase the kinetic energy of the drop?
Yeah, for example, by heating up the droplet and dropping it in a higher height.
Oh, we did it. Yeah, to increase the impact speed, and we said increase the normal number.
Okay, and I
Opponent, please put your microphone closer to your
sorry. I would also like to suggest another way to examine this, which is using a modified Weber's number. And what does this do? This basically means you're accounting for the total energy, kinetic energy of the droplet over the energy of the surface. And if
sorry. Can you make some space so others can see your
droplet? So if this number is really big, that would mean that you have more kinetic energy in the droplet than the energy of the surface. Thus, this can account for why the splashing happens because there's more kinetic energy allowing the splashing to occur. So when you drop it at higher heights, did you notice that there are more splashes?
And this is a here because the normal number is affected by impact speed, and which is you just said the kinetic energy. So as you can see, and like here in the higher tangential number, as the impact speed, which is the normal number increase, it will transform from rebound to partial rebound, which is that statue.
Another question from class is, did you guys test the viscosity of the droplet?
No, we didn't, because we think the viscosity is only affect the coefficient of the surface tension and also the density. So we didn't measure that.
I think the viscosity of the droplet actually matters in this case because if, say, you were using water for your original droplet, right? If you add, like, say, your solution becomes 60% sugar, right? Then I think the sugar would increase the strength of the intermolecular bond within your droplet. Thus, it would make it make the surface harder to tear apart. So I think increasing the viscosity of the droplet is very impactful because it determines how long or how easy
Yes, agreed.
Another thing I would ask is the surface material. I realize that you didn't change anything except for your PVC. What do you think would happen if I change the surface to a more porous material? Meaning the surface is something like paper with little holes in it.
You mean? And in a kind of like you just mentioned, it will affect the static friction and make friction be larger, and so the rebound is more hard for the droplet to rebound.
Okay, I guess my question is, for now, how do you determine whether the droplet is attached onto the surface?
You mean that?
How do you specifically define whether the droplet is reflected or not reflected?
Reflected means after the droplet touches the surface, it can maintain its shape. And not reflected means it can maintain its initial shape, like the partial rebound, it just flashes. And the deposition, it didn't refer to any severe shape. It just has a line of water.
For all your trials, you notice consistent shapes of the droplet.
Sorry, again?
So for every single one of your trials, you notice consistent shape in your droplet.
You mean after or
no? When it first hits the surface of the droplet, because you're using a PVC, right?
Yeah.
Attraction would be like this, where the droplet stays on the surface instead of rebounding, like you said, right?
No, in our theory of rebounding, the droplet only touches the bottom of the droplet. Only the bottom of the droplet touches the water and taken by the water. So here will be a space for the air bubble layer to go.
But if your kinetic energy of your droplet increases, the maximum spread of the droplet will also increase, right?
Yeah. About the kinetic energy increases is just a normal Weber number. So it will become partial from rebound to partial rebound or deposition.
But I mean, you did notice the greater spread of the droplet, right?
Yes, when it happens to deposition or partial rebound.
So once again, if I'm talking about no rebound, what would the droplet look like? How would you define not reflected? You would just analyze the surface and say that it's sticking onto the surface, and that would count as not rebound.
We found that you mean a non-rebound is partial rebound or deposition?
No rebound at all.
Just like deposition.
Yeah,
we can't see any flashes, reflected from the surface. Just all the water from the droplet stays on the surface, and we can see clearly in our photo.
So I would like to know the boundary for your partial rebound. What would that mean? Parts of the liquid rebounds.
Yes.
How would you quantify the amount of liquid that is being rebounded?
We didn't quantify the amount of the liquid rebound.
So even if the rebound droplets, like 99% of the volume stays on the surface and only 1% rebound, you count that as a rebound. How can you accurately see that through a slope of count?
We can. The partial rebound means we can obviously see the droplets separate different pieces.
Right, thank you.
So now will be the time for the opponent to make summary of the discussion for 1 minute, please.
So thank you for the reporter for a very good discussion. We talked about how changing a few relevant parameters may affect the phenomenon, such as changing the viscosity of the droplet, or how increasing the kinetic energy of the droplet may result in different types of rebound. One comment I would like to make is perhaps they can try using a porous surface. The reason why I would suggest this is because if you use a porous surface, you can actually see whether the droplet is making the surface wet. And to determine this, you can spin the surface at a very fast velocity until, if you drop the droplet, the surface is no longer wet. One of these surfaces I would like to recommend is, for example, paper, because you can very easily determine whether the paper is wet or not. And that would be like acting as a critical angular velocity for a specific droplet to rebound. And I think that is my summary. Thank you.
I would like to ask presenter of the reporter and opponent to stay on the stage and get ready to answer the question from the reviewer for 3 minutes. So please start.
Okay, for the report, can you give me the critical boundary of the droplet to reflect, just like the critical velocity of the surface?
We can give you that because with the parameter we do is the radius of the drop or in the velocity. But you can see here in the Weber number of the droplet.
Okay, and then the minutes. Okay. So for report, please turn to your definition. Please turn your definition of the string kind of rebound. In which kind of condition do you mean assume that is the reflect? Just like the following statement and definition.
Parallel round and rebound or reflect.
Okay, thank you. And can you tell why the air flow is for existing? While the air boundary wall is existing, can you explain why it was existing?
You mean the air boundary layer?
Yeah.
Because there has a drag force between the air of between the horizontally moving surface and the air.
Okay, get the finish. Do you agree with the report?
I agree with the reporter that no matter what liquid you drop, there will always be a thin layer of vapor between the liquid and the solid, or a solid and the solid.
Okay, thank you. And so for report, do you think the most of the area of the droplet on the surface, there will be most area will be not contact with the surface, right?
It rebound. Yes.
If that rebound.
Yes.
Okay, so the most area will be above the air boundaries.
Yes.
Okay, so can you explain why the air boundary will give the lifting force to the droplet that it rebound?
Because there's a contango between the droplet and the moving surface. So the air boundary will give it a lift force.
Okay, thank you. And do you think for that one, do you think the lifting force is on here?
I think because the wind speed at their surface is very inaccurate and unstable, as we stated, I don't think they can use that as an examination.
Okay, so can you explain why is the lifting force from? Just like the droplet to start the rebound.
Can you explain your question again?
Why is the force that the droplet started to rebound? Because you said the air boundary there was not the main force.
No, I didn't say it was the main cause. I said that because it's unstable, the reporter can't use that. Because they can't determine it's stable.
Okay, I got your image. And so for report, do you think that acting points of the droplets on the surface will determine the result?
Sorry again?
The droplet acting points on the surface will determine the result. Okay, thank you again.
Do you mean like the droplet time on the surface?
Yeah, do you think it will determine the result?
I think the droplet time will, yes, because higher kinetic energy means greater spread over the surface, and that would mean a greater time to achieve that spread.
Okay, thank you for the reporting.
Thank you.
Okay, now following will be the time for reviewer to prepare their presentation for 2 minutes. Okay, reviewer, I would like to ask you to stay in the center of the stage and please start your presentation.
Okay, I don't know there is a lot of competitors. And the reviewer contains here in today's I'm going to review is problem number 14, dynamic hydrophobics. And here's the first thing. When a droplet of liquid impacts on horizontally moving surface, the droplet may be reflected off. Depending on the speed of the surface, investigate the interaction between the moving surface and the liquid drop. And on that also be what the liquid drop will reflect after impact, and how the speed of the surface will determine the result. And here's the report online. First, in the fundamental part, reporting show that having defined three kinds of motion, which is the partially reflected, rebound, and disposition. And the third part having considered the drop impact on the surface, and using a surface tension and the Weber's number to describe the phenomena. And the third part having shows that the electrical setup, and also show the property of the moving surface and how does the moving surface determine the Weber's number. And I think the report having clear definition about the reflector, because they have three kinds of definition. Also, they will present a lot of phenomena. Also, the main cause of the reason of the phenomena for why the liquid drop will reflect is well extended. But I think they only gave the quantitative explanation of why the liquid drop will impact and didn't give the critical boundary condition. And also, the theory was too brief to display phenomena just like I previously mentioned. And that was a connection between the experience and reaction model. And also didn't show the calculation of the Weber's number, and also lack of property, because it only shows that how the moving speed depends on the Weber's number, and also that there is very one lack of the reproducibility. And here's the opponent's presentation summary, that the opponent having mainly as well the static friction, which is the fact the flipping of the droplet, also the behavior of flapping, splashing, and the other effects and the fact, and how does the surface tension, rebound, and their relation between the energies. And in the course of the report, that we point out the lack of quantitative distinction in the report. Also, that in the very prediction that you were the way to quantify the proper statement. But I think they count for opponents that they didn't have a boundary condition that the phenomenon will happen. Also, there is lack of the discussion on the important property, which is like there are lack of the discussion on the viscosity. Also, there are too many irrelevant factors discussed. And also misunderstanding of true words dimension mentioned in the report. And here's the discussion, which is the formation. The opponent asked will the volumes of the droplet change during the impact. And report answered no, it will remain severe shape. And the opponent disagreed with the report that the impact of the droplet will be caused the deformation toward the droplet falling down. And also here's the contact angle. The opponent asked how to establish the rebound contact angle. And report answered to control that the contact angle is 90 degrees every point. And reviewer believes the project of the report. However, air resistant jet force might cause the deformation to cause the droplet. And also, in the vapors and the viscosity, the opponent asked, do you think the vector is the important factor of the result? And report answered the main reason of the phenomenon is the surface tension. And reviewer believes that it's not an important factor, and we think the viscosity of the droplet is more important because it will influence the shape of the droplet. And here's the performance of both the reporter and opponents. And we think the reporter can achieve the final statement which causing the air film by the surface, and also they can well explain why the droplet was separated in few times position. And air film quantifies the shape, size of the droplet, and also the thickness of the air film, which is mentioned in the report. And also lack of the discussion on the boundary condition to that the liquid drop reflected. And also lack of discussion on the air film flows types just like the linear flows or turbulence. And what here's my presentation. Thank you for listening.
Okay, thank you. So, following will be the concluding remark of the reporter for 2 minutes. So, please start.
With the boundary
sorry. Please stay in the stage.
The bar and the critical velocity is showing the region and future. So, and we agree that the other kind of Weber force that the opponent mentioned is quite useful. It's just another form of our original Weber number. And also we define partial rebound in our experience to only show a transition between deposition and rebound. And we can extend which kind of rebound it is easy by checking the instance of the connecting. area because we can obviously see there are several splashes splash out of the droplet and reflected. And so this is the end of my concluding remark. Thank you.
Okay, so I would like to ask all three presenters to stay on the stage and get ready to answer the question from the juries. So any jurors want to ask a question? Okay, please.
I just wonder, you use the circulating surface, the bag. I wonder if in either experimental aspect or the regular aspect, the traditional moving surface or the circulating you use is better. Is the language or the language, please?
I think it is easy for a way to create a horizontal moving surface because it is only in one direction. It's hard to create, and also because the droplet is very small, so we can assume that the places that the droplet touches is horizontally.
I believe that using a circular disc.
Sorry, do you expect any?
Yeah. I believe that using a circular disc will definitely be a source of error because, as the reviewer has mentioned, the droplet time may impact whether the droplet is moving in a circular direction or not. And I believe by using a belt to conduct the experiment would be much more clear and easy to examine.
Sorry, reviewer, can you move into the?
Okay. So I think that is needed that you use in circular motion that the droplet will not be just two-dimensional motion. You have the three-dimensional motion. You will have the horizontal displacement. And also the former statement having mentioned use the horizontal surface. So I think using the opposite way it will be more proper.
Yeah, please.
Reviewer also point out whether the airflow is important to make the droplet cool down. So I'm curious, for example, proponent and reviewer can elaborate on this whether the airflow is important. Because in the reporters discussion, we think airflow is very important, critical to push the droplet to relax. So can you comment on this one, whether airflow, what's the role of the airflow in this problem, the interaction between the surface and the liquid droplet?
I think airflow is very important because it will reduce the contact area of the droplet and the surface. And if the contact area becomes smaller, it will be more easier to reflect it and not deformation on the surface.
I believe that one major aspect of having a thin film of vapor between the liquid and the surface is that the thin film of vapor is basically basically acts as a propulsion between the two, so that the two of them are not directly contacting with each other. And I think the reason for that is because as the liquid droplet gets closer and closer to the surface, the electrons will start repelling each other, so they're quite touch, or if you know, bond. That's what I mean.
Okay. So any further question? Yeah, please.
So I have one question to the. My question is to you. So you spend some time. Opponent, so you spend some time discussing with the reporter about the contact angle. Okay. So can you give me a very short answer about what kind of property of the materials will affect the contact angle?
I don't think the material would affect the contact angle. I think the contact angle would change depending on how you drop the droplet. Like the relevant parameters such as the, I guess all parameters may affect the contact angle a little bit. But I don't think the change in that angle will be too much of an effect.
Okay, so I think we can move on to the scoring part. Okay, so all the jurors, please show the mark for the reporter. I will read from my right hand side. So the scores are 7, 7, 7, 7, 6, 7, 6, 7, 8, 7.
Thank you.
And the score for the opponent. 8, 7, 8, 7, 6, 7, 8, 8, 8, 8. And the score for the reviewer are 9, 8, 9, 8, 7, 8, 8, 7, 8, 8.
Thank you.
Okay, so I think the scores are quite even, but we are welcome for some comments. So anyone wants to give some comments?
I will give some comment to the opponent. So I think although the most the points I subtract is from your speech, your presentation part, because actually you have still about 1 minute, about 90 seconds left on your in your presentation time, which means, from our perspective, that you spend too little time for the summary of the reporter's report. So, which cannot give us a clear picture to know if you really understand the main points of the reporter's report. So that was a pity in your whole presentation. So, and also during discussion, as I mentioned, you spent some time talking about the contact angle, and I think you should try to make out what kind of physics that you wish to discuss. That will help you to have a better, first, a better scores, and secondly, to let us have a better understanding of the topic. Okay, that's my comment.
I'll take it to that. Thank you.
Okay, so any further comments? Did you get the point? Okay, so I think since there are no further comments, I would like to close this section and we can have a 10 minutes break. So please come back in 10 minutes. And during the break, I would like to ask all three teams to change your seat.
了解部分。高中跟上不错哦，好不好？好不好？
有资深。
Okay, welcome back to the second round. I see all the jurors are ready. Reporters seems okay. Opponent, are you okay? Okay, and viewer, you are ready. Okay. So let's start the second round. The second round, the reporter will be all-nighters. And opponent will be Excelsior, and reviewer will be Miracle. The problem to be presented will be number 4, wind speed. So we start from the preparation of the reporter for 5 minutes. Please start. Clark, please start. Thank you.
I think I'm ready to begin the report now.
So you want to start now? Okay, so we start the presentation for 12 minutes.
Good morning, everyone. My name is Jonathan Bruce from Team All-Nighters, and I'm going to be reporting problem number 4, wind speed. So let's begin with an examination of the problem statement. Let an electric current flow through a coil. When cold air flows over the coil's temperature will decrease. Investigate how the temperature drop depends on the wind speed. What is the accuracy of this method of measuring the wind speed? So this problem, in the reporter's opinion, has 3 main components. How is the heated coil cooled? What is the relationship between cooling and wind speed? And what are the relevant parameters that affect the measuring accuracy? So here's a quick outline of my presentation. I'm going to go through phenomena investigation, where I examine the material properties and the conceptual theory behind the cooling, as well as a theoretical model, experimentation and discussion, and finally a quick conclusion. So let's begin with phenomena investigation. So this problem is describing a hot wire anemometer, which is a device that relates wind speed to the temperature of an electrically heated wire in a fluid stream, where the temperature is determined from the resistance of the wire
typically using a Wheatstone bridge setup as demonstrated there. However, in our experiment, we utilize a hot wire anemometer that measures the wire temperature directly using a thermocouple. And we feel that this gives us more direct measurements and greater accuracy. Basically, the conceptual explanation of the phenomenon is that the ohmically heated wire is convectively cooled, and our goal is to ascertain the effect of wind speed on the wire temperature. So there are a couple of assumptions that we used in creating our theory for this problem. So the first is our model for convection, which is that thermal equilibrium is separately obtained both uniformly inside the wire and within a distance W/2 from the wire around its circumference. And we also assume that conduction and radiation to the surrounding air is negligible here because convection happens at a significantly greater rate, and we will demonstrate this in the next couple slides. And we also assume that there's no oxidation or change in the material properties of the wire over time, because the wires that we used were made of nichrome, and most metals, when they're heated, they tend to oxidize, which affects their properties and interaction with the air. But when nichrome is heated, only a very thin film of chromium oxide is formed on the surface, and it preserves many of the properties of the material. So let's begin with our first assumption, which is the model for cooling. So typically, we would model the diffusion from the wire into the surrounding air as such. However, to simplify this for this problem, because we observed that only the air at a relatively small distance from the wire relative to its radius is actually heated up, we assume that a thermal equilibrium is achieved in the air within a distance W/2 from the wire, and that the temperature within this region is constant. So it's basically just a simplification for our theory and for our modeling. And we actually found in our fitting and experiments that this is a quite good approximation of what actually happens. And our second assumption is that we can ignore heating, cooling due to conduction. And plugging in some of the parameters that were used in our experiments, we see that even the smallest ratio between the rate of cooling due to convection and the rate of cooling due to conduction is around 200. So convection is at least 200 times greater than conduction, or 200 times faster than conduction in all of our experiments. So we find it safe to ignore conduction in the majority of cases, as we'll discuss later. And our third assumption is that we can ignore cooling due to radiation. So there are all the relevant values that are needed to determine cooling due to radiation for this wire, including the emissivity of nichrome. And we can see that when we plug all these values into the ratio there, we see that the minimum ratio between the rate of cooling due to convection and the rate of cooling due to radiation is around 350. So the rate of cooling due to convection is at least 350 times greater than that due to radiation. So we, again, find it safe to neglect radiation. And we also attempted to measure the wire resistance versus temperature. And you can see that the curve there demonstrates a linear fit in accordance with what the theoretical equation for resistance versus temperature would be. You can see that there's a bit of variation and error in the data there and a relatively low R-squared value. That's just due to a lower number of significant figures in our current measurement than we would have liked. But you can still see that's approximately a linear trend. And moreover, most times the wire was heated much less than around the maximum value you see there, about 200 degrees Celsius. But you can see that even over that range, the increase in resistance is rather small. So we assume a relatively constant resistivity here. And this allows us to derive the temperature-velocity relationship for the cooling of this wire. So we basically assume that the rate of ohmic heating for the wire is equal to the rate of cooling by convection using the formula MC delta T, but modified in terms of the amount of heat absorbed by the air moving past the wire. And we can see that the volume of air heated is going to be equal to W times the length of the wire we're looking at, times the velocity of the air, dt. And using these assumptions, as well as, again, the ohmic heating value for the wire, we can come up with this governing equation for our theory here. And again, perhaps I should explain that the effective width W is basically just where we assume that the temperature is constant at a certain distance from the wire to heating. And we use this as a fitting determine this from our experiments. And also the problem statement notes that we must consider the accuracy of this method. So since we're predicting a linear relationship there between the delta t, between the wire and the ambient air, and then the 1 over velocity of the air, we are judging accuracy as the linearity of the delta t versus 1 over v graphs that we're going to obtain from this experiment. So here's again the governing equation and just a list of some of the variables that we're going to consider. So the relevant parameters that we're going to change here are current, the wind velocity, and the wire cross-sectional area, as well as a couple others that I'm going to explain later. So let's move on to our experiments and results. So as I mentioned here, our experimental setup schematic is as follows. We have a DC power supply connected to a nichrome wire, and we have a thermocouple temperature probe directly attached to this nichrome wire. And because we recognize that the thermocouple probe can also be cooled by the air from the fan, we are setting this thermocouple up to measure voltage instead of temperature using a very, very high precision voltmeter, and then we're converting that measurement to temperature using a Python program. And the air is supplied by actually a dedicated air supply unit with a very long hose on it. I will speak a little bit more about this on the next couple slides. And this can be repositioned relative to the wire. And finally, we confirm the measurement of the wind speed using a typical fan anemometer. So again, some of the independent variables we're going to test are wind velocity, current, as well as the orientation of the air supply relative to the coil of wire, as well as the wire thickness. The dependent variable is always going to be the temperature difference between the wire and the air at thermal equilibrium. And the control variables, we're always using nichrome, which is 80% nickel and 20% chromium. And the ambient air temperature is always going to be 21.5 degrees Celsius. So I mentioned that we're not using a typical computer fan, and we're instead using an air supply unit here. And because a typical computer fan creates quite a bit of turbulence and eddy currents, and the flow is sometimes slanted off to one side, so it's directional, we feel that this, which provides a very highly directional airflow as well as a bit less turbulence, is a better apparatus to use instead of a typical fan for this experiment. And as I mentioned, the wind velocity measurements were measured by a handheld anemometer, and we determined the voltage and temperature from the thermocouple. So first we're going to verify the theoretical relationship that we examined there of temperature versus current. So as you can see from the equation, delta T between the wire and the ambient air should be directly proportional to the current squared, and we see this with our experimental data, and we see no significant deviations from our theory expectations, and the relationship is very linear, so we see that this is a pretty accurate method for measuring, for quantifying this relationship according to our definition of accuracy. And we also verified our assumption that delta T is directly proportional to 1 over the air velocity, and we can see that once again this is a very linear relationship that provides a very accurate method for measuring the wind speed. We see that there is some loss of accuracy, some nonlinearity at very, very high wind speeds. And we think that the possible cause of this is some greater turbulence from the air supply as the Reynolds number increases to a very high amount that could affect some of the cooling characteristics. So once again, we see that there is in fact a linear relationship between T and I squared as well as T and 1 over V according to our theory. And we suspect that turbulence is the cause of some loss of accuracy. So now we move on to changing wire thickness. So you can see here that we have a graph for a 0.5 millimeter radius wire, as well as a wire with radius 1 millimeter. And we can see that the thinner wire appears to be more accurate. The trend appears to be more linear, and the error for the slope, as well as the deviation of the points, the R squared value, appears to be a lot less. And why is this? Well, because remember, one of our theoretical assumptions is that thermal equilibrium is achieved uniformly inside of the wire. But if the wire is too thick, it may be much harder to achieve this uniform temperature distribution inside the wire. The center of the wire may be hotter than the outside when the outside is being cooled by the airflow. Whereas a thinner wire may have a more uniform temperature distribution during the cooling, and therefore will align better with our theoretical results. And additionally, we need to use the wire orientation relative to the air source. So we can see that when we place the coil of the wire parallel to the air source, the greater amount of air and some loss of accuracy compared to if we place the wire perpendicularly to the coil. So the perpendicular orientation appears to be more accurate and more precise. Now why is this? Because first of all, the air moves past the wire. We calculate the Reynolds number, and it is high enough to where, because of a cylinder and an airflow, it will produce a von Karman vortex stream at this value of the Reynolds number. And this turbulence may affect some of the airflow over further segments of the wire down the coil, as seen there. But no such effect will occur for the perpendicular orientation because the air is not flowing over any more wire after it flows over. And also we see that there might be some initial heating of the air traveling over the first parts of the wire before it moves backwards, so that might also contribute to some of the air. So some further, we can skip this. And then let's just go on to our conclusion. So once again, we used an effective distance from the wire for modeling the cooling, and we only took convection into account, and we tested multiple different parameters. Thank you.
Okay, thank you. So now is the time for the opponent to ask short questions, so please start.
Thanks for the presentation from the reporter, and I have a question for you. And the first one is, when you're calculating the power from current, you can calculate it with the gain effect of the current on the power supply.
Sorry, can you repeat the question?
Did you calculate the power from the power supply, including the gain effect of the current that was affected on the power supply?
Oh, well, we calculated the power produced by the coil of wire as I squared R, so if that's what you were asking.
So where's the how do you measure the resistance?
We measure the resistance using
the power supply.
The voltage divided by the current.
Can you answer my question?
Yeah. The resistance of the power supply. We just use a DC power supply to pass a constant voltage through, and then we divide the voltage by the current to get the resistance of the coil. I don't necessarily answer the question.
Thank you. And the next question is, did you consider the expansion of the coil during your experiment?
Because the coil was so thin, it usually kept the temperature of the coil at around 100 degrees Celsius or below. We didn't really consider thermal expansion to be fascinating.
Can you repeat your answer again?
We didn't really consider thermal expansion as a very significant phenomenon in our experiment.
It wouldn't affect the results?
Not that much. It would certainly be some effect, but not that much, rather negligible.
Okay, thanks. Did you measure the temperature of the wind during your experiment?
We just assumed that the temperature of the wind was equal to the ambient temperature of the room because our air supply draws in air from outside.
Okay, I got it. Thanks. And will it affect the power bring up by wind, the temperature of the wind? Does that affect the results?
Well, I mean, sure, there might be some variation in the temperature of the wind, but I already mentioned that as a source of error when the wind is blown parallel to the coil.
Because you didn't show us a picture or a specific video about your experimental setup, so I want to ask you, what do you use to calculate the measure the coil's resistance?
Measure the coil's resistance? As I said, we just use the power supply readouts. We divide the voltage of the power supply by the current passing through the system.
Okay, thank you. So time is up. So following will be the time for opponent to prepare. Okay, I think it's almost time, so please start your presentation for up to 4 minutes. Any remaining time will be added to the discussion, so please start.
Among the regional competitor, I'm the opponent from Team Excelsior, and today I'm going to oppose problem statement number 4, which and here's problem statement. That an electric current flows through a coil. When cold air flows over the coil, the coil temperature will decrease. Investigate how the temperature drop depends on wind speed. And what is the accuracy of this method of measuring wind speed? And according to the problem statement, I think the reporter should mainly focus on how to derive wind speed from coil temperature, and also what parameters will influence accuracy. And as this is a kind of complex question to solve this problem, so I think I may have a structure of solving this problem. First, we'll discuss the temperature dropping process, which will include the heat transfer during the experiment and also the power equilibrium. And then we will measure the temperature drop at different circumstances, which should be included the initial temperature of the coil and also the wind velocity and also the power that was supplied from the appearance. And then we can define an accuracy that should be able to explain whether the derived value of the wind speed is correct or not. And then we can predict the wind speed by the equation that you find in your report. And then they should also mention the measure limit of your measurement, because since that the problem statement has mentioned that it is a method of using to measure the wind speed. And here's the strong and weak points of the report. First, they have a very clear explanation about each transfer during their experiment, but they didn't show any observation video of the phenomenon or fixing insights that I couldn't make sure that their experimental data are correct or not. And they have poor explanation for why radiation conduction can be ignored, and also their lack of clear definition of accuracy. And overly simplify the problem during the assumption of fluid cooling, and they didn't explain the deviation to material-like experiments very well, and they only tested a few parameters, and they didn't control the distance between the air vent and the coil, which will affect the velocity of the wind. And but they also have a good program used to transform the temperature to wind speed and the deviation for and let's move on to the points to be discussed. First, in the theory part, I would like to discuss about the power input by the current. And the first thing is about the calculation of power input. And I asked them before in the short question time, I asked them, do they consider thermal expansion? And the report answered me that they didn't consider it. So I would like to discuss about it later. And as they mentioned that they ignore the thermal expansion. So, the thermal expansion affect the resistance during the experiment. So that, the power input affected by the resistance change during the experiment. And also, I would like to discuss about the power bring out by convection, which includes the power Newton's cooling law and also the wind temperature and also the wind speed, and the surface area of the coil is going to affect the power bring out by convection. And I would like to discuss about the definition of the accuracy of the method of measuring wind speed, and it should be able to explain whether the derived value of wind speed is correct or not. So they should be transform the temperature deviation into the speed accuracy, and they should mention the error range between the theoretical model of wind speed. And they should also mention the boundary condition of the measure limit. And this is the experiment, and they also mentioned that they have a material selection that I think is pretty good. They use nichrome as their material of the coil, and I would like to ask them what is the benefit of using this material, and also the increased resistance during the experiment, and what will be the effect. And the contact resistance while measuring the resistance of the coil. And here are some parameters that might affect the result of the experiment, which included the initial temperature, wind speed, power supply from power supply, and the surface.
Sorry, time is up. Please start the discussion.
And for the question for the reporter, as you mentioned that you use I squared times the resistance to calculate the power input by the power supply, right?
Well, that's the rate of ohmic heating of the coil. So the rate at which it transfers heat to the surrounding area.
Yes. But you mentioned that you include the power supply into the resistance, right? You also include the resistance of the power supply.
Well, I mean, perhaps I should clarify what I mean here. The power supply that we use is basically like a DC power supply.
Yes.
So it provides both voltage and current readouts. So we just use the voltage and current readouts in connection with the wire coil to determine the resistance of the coil.
But as I mentioned, heating effect on the power supply affect the results. Why don't you just measure the resistance of the coil? But you include all of them.
Well, we did measure the resistance.
So the cooling thermal should be only effect on the coil.
Yes.
It wouldn't affect the power supply.
No, it wouldn't.
Yes, but when you're calculating the power that was applied from power of the current, you include all of them, right? So is it correct to include the power that affected by power supply?
Well, there may be a very small internal resistance here, but the only resistor in this circuit is very low. Maybe very slightly, but not that
very
much.
small. But you didn't mention that in your report, right? Can you prove that it is very, very small since that you didn't have any experimental data that proves this?
Well, this power supply supplies a constant voltage and a constant current, so I'm not entirely sure what you're asking. I think, the only significant resistor in this system is the coil.
So, as you mentioned that you didn't consider the thermal expansion of the coil, right?
No, we didn't.
So, according to the Newton's cooling law, the surface area of the coil is going to affect the power bring on weight, right?
Yes, it was.
Which is the convection. So,
yes.
You didn't. Will the thermal expansion affect the loss of the coil?
Excuse me for a second. Could you please turn to, for example, slide 20? Okay, yes. So you can see the temperature difference between the coil and the surrounding air, and the surrounding air is at 21.5 degrees Celsius. And you can see that the temperature difference in most of our experiments is always around 25 degrees Celsius or less at equilibrium. So at those temperatures, which are 50 Celsius or less, we don't think thermal expansion is that significant.
Okay, so you just didn't prove that the thermal expansion would affect the result. You just say that your experimental data is correct, but you didn't have any theoretical model that proved that the thermal expansion would affect the result.
Okay, well all I'm saying is most of the time the equilibrium temperature of the coil is 50 degrees Celsius or less. In that temperature range, I don't think we need to consider thermal expansion as that significant of a factor. If the coil were a lot hotter, then yes, but in this range, not really.
Okay, so may I ask, so you mean that you can prove that the thermal expansion would affect the result a lot through your experimental data?
Yes, we didn't show the calculations, but we can prove that.
You didn't show us any experimental setup and any observation video. How do you prove that the experimental data are correct?
Okay, well I apologize for not showing an image of the setup. I agree that would have been a good inclusion, but we didn't observe any significant thermal expansion, so I'm not exactly sure what you're asking here. We didn't observe it in our experiments. It shouldn't be that significant in this temperature range, so why should we include it in our theory, except it's maybe an error correction factor?
Okay, got it. So just do that. So
yeah, because we thought it wasn't significant.
Okay, as you can see, in your experiment, you include the resistance of the coil, right, to calculate the power.
Yes.
Okay, and then will thermal expansion affect the power effect from the power of the current?
Let's turn to slide 12. Okay, as we see here, even when the coil is heated up to temperatures that far exceed the temperatures used in our experiment, as I mentioned, the equilibrium temperature of the coil is about 50 degrees Celsius, but we heated it up all the way to 200, and we saw that the resistance only increased very slightly. So I think this is also further proof that thermal expansion is rather negligible.
Can you explain why there's a huge deviation from this theoretical line?
Well, the huge deviation from the theoretical line is probably due to the readouts that we used, because we would have liked it if our power supply provided more significant figures for the current, but unfortunately we were only able to use the readouts. So there may have been some error caused by that.
You think the thermal expansion would affect the resistance?
Well, no, because as I just said, even at very, very high temperatures, the resistance only increases a little bit. So, and most of the temperatures used were much, much smaller than 200 degrees Celsius. So,
okay,
your
experimental data, but you can prove it through any experimental theoretical model?
Well, I think we just have proved it through experimental data. We showed that even at very high temperatures, there's very little change in resistance.
Okay.
Yeah.
So, as you mentioned that you didn't consider the expansion, so will the power bring out the wind that will it affect the power bring out wind?
Will it affect the I'm sorry, could you rephrase the question? I'm not sure I understood that.
As you say that you didn't consider the expansion, so you mean that the surface area of the coil would change during the experiment, right?
Yes, we assume it doesn't.
Okay, so actually in the real world, the surface area is going to change a little bit.
Yes.
Will that result?
Well, we we think it might have a very slight impact, but as we mentioned, the thermal expansion should be rather negligible here. So it would have some impact, but it would not be terribly significant.
Okay, thank you. When I have another question to ask you. When the wind speed is too small, too slow, will it affect the accuracy of your makeup?
Could you please turn to slide 26? Okay, I'm sorry I didn't quite have time to go over this in my report, but yes, we think that very slow wind speeds will affect the accuracy for two main reasons. Because the slower the wind speed, the more significant the effects of conduction become. As I mentioned, the ratio that we calculated between convection and conduction, rate of cooling, is about 200, but when we slow that down to the very slowest wind speed we tested, which is 0.8 meters per second, that decreases to about 55. So we think that conduction will become more significant if it's slower wind speed or no wind speed at all. And we also measured the drop in wind speed.
But I think it is because when the wind speed is too slow, the temperature of the coil is going to be mainly affected by the free convection. Do you agree?
Yes, I just said I agree with that because the effects of conduction will become more significant. So yes, as the convection, as the rate of cooling due to convection decreases or free convection starts to happen, then yes, it will become less significant.
According to the problem statement, you should define the accuracy, and where's the definition of accuracy?
Well, we did define the accuracy. Could you please turn to slide 13? Yeah, sorry, but can't be seen there. It's kind of hidden by the whiteboard. But the accuracy we defined is the linearity of the graph. So we measured that by how well the points line up with a strict line, as well as the R-squared value. Because our theory should predict a linear relationship between, for example, temperature and 1 over V. So we're defining how accurate is that linear relationship as to model the actual relationship between the two.
Okay, so then how do you say that your experimental data is valued and define accuracy?
I just did define accuracy as how linear the line is. For example, could you turn to...
Can you show me the slide?
Slide 22, please. So like, for example, we can compare these two. We can see that the 0.5 millimeter radius wire is defined as being more accurate than the 1 millimeter radius wire because the points adhere to the line more closely and the R-squared value is higher. That's our definition for accuracy. Yes, it does, because we think that the closer that the points on our graph are to linear, the more accurate the measurement is. So we think that we have considered the problem statement in this case.
Did you have any experiment about how broader affect the accuracy of the method?
Well, yes, I mentioned a few. First is this, changing the wire radius.
Yes.
We also mentioned...
it seems that it didn't change very much. What's the difference?
It seems that it didn't change a lot. Okay, well you can see we used a 1 millimeter radius wire and a 0.5 millimeter radius wire. Yes. So...
what's the difference?
Well, what's the difference? We can see that the R-squared value on the right is higher. We can also see that the percentage error for the slope is lower. So we can see that the points line up better with a linear trend as predicted by our equation. So we define that as more accurate.
So it is, you only done these two experiments?
No, we've actually done another one. Could you go to slide 24? Yes, we've also compared the accuracy versus the orientation of the wind source relative to the coil. And you can see that when the wind source is perpendicular to the coil...
Thank you for the explanation, and I would like to ask you why you choose micromass your material for coil.
Okay, well again, as I mentioned in the very beginning of my presentation, most materials, metals especially, tend to oxidize when heated, but nichrome, this oxidation phenomenon, is less, so the property of the material will change less when it's heated, so it's more accurate for this experiment.
Okay, thank you. So you mean that the resistance of the coil is not going to affect very much because the resistance change during the experiment is not going to affect very much because you used it by...
Sorry, the time is up.
Yes, I measured it very
Sorry, please stop.
Sorry.
Since your question is not finished, so I think the stop is quite okay. So please give your summary and please restart the clock. Okay, please. Can you reset this clock? No. Yeah, please.
Okay, and I'm going to start my discussion summary. First, we discussed about thermal expansion should be considered since that is that the experimental result greatly and the report had no result that is negligible whether they would say that their derived value of wind speed is accurate or not. And the report did not have a proper explain of the assumption that they ignore conduction and radiation, which are factors that they should be considered. And this is the end of my discussion summary. Thank you.
Okay, reporter, please stay on the stage. And now is the time for the reviewer to ask questions to the reporter and opponent, please.
Okay, so we noticed that you use thermal coupling to monitor the temperature of the coil. But do you make sure that the characteristics of the thermal coupling is similar to the characteristics of the coil? Do you think there will be a lag caused by the conduction rate of thermal coupling?
Yes, there would be a very small lag rate caused by that. However, as I stated, we're measuring this at thermal equilibrium, so that might be an issue for how fast the wire cools down, but not the end temperature that the wire reaches as we're investigating.
Oh, so you don't care about how long it takes to get the temperature and the readings?
No, because we're looking at thermal equilibrium here.
Okay, and we noticed that in your graph there's no error bar. Why is there no error bar?
Yes, good question. So, as I mentioned, our power supply readout for the current has very small numbers of significant figures, so we would have liked them. However, our voltage measurements using the thermocouple, for example, were accurate to 4 significant figures, and the anemometer was accurate to 3. So we calculated those values, and the error is so small that the error bars would be negligible in this case.
Okay, so is your power supply a constant voltage or constant current?
We set the power supply to a constant voltage, but as we mentioned, the resistance of the coil does not change significantly, so we can also assume a relatively constant current.
Okay. So, did you try using a different width of the coil to explore effect of vortices?
Different width of the coil? Yes. We didn't try that. As we mentioned, there could be some vortex streaks formed behind the coil when the wind flows over it, so we think that may be a relevant parameter.
And do you have any theoretical prediction? Can you tell, if I give you a change in temperature, can you give me the wind speed?
Okay, well, as I mentioned, could you turn back to slide 13? So, as I mentioned, the effective width here, W, is used as a fitting parameter, so we have to fit it to the graph, but once we fit it and obtain that calibration curve, yes, we can obtain the wind speed from the temperature difference very accurately.
Okay. So, we noticed that you only have a few dots, and you use those dots to fit a linear regression line. Why do you have so few dots, so few experimental data?
Well, in our opinion, we have enough data points to accurately fit a line. We acknowledge that we could have tested more, but we think it's sufficient.
Do you think the data is sufficient? No. Yes, because we noticed that you use those two dots to determine that the relationship is linear, but if you plot more dots, the relationship might not be that linear. So, next question. Can you explain how Reynolds number affects the convection rate?
Okay, well, as I said, if the Reynolds number when the air is flowing around the cylindrical coil is high enough, then it would form the vortex streaks behind. So this may affect the flux of air flowing over the remaining sections.
Okay, thank you.
So following will be the time for opponent reviewer to prepare. Okay, reviewer, please start your presentation for 4 minutes.
Okay. Good morning, dear judges and fellow competitors. I am Arthur from Timber, and I will be reviewing problem number 4, wind speed. So because the reporter stated the problem statement, I won't go over it again. So we think the main factor to be how the temperature of the coil is affected by the wind blowing over it, and the accuracy to measure wind speed with this method. So this is the summary of the reporter. They said the phenomenon. As wind blows over the coil, it cools. And their theory is that the convection of heat transfer takes the energy out of the coil. And yes, and they measure it with the thermocoupling and they fit it on a reversion line to determine the velocity of the wind speed. And in their experiment, they had a DC power supply and they measure temperature with the thermocoupling just like I said, and they use the different thickness and the wind speed of the change these two parameters. So for the pros, they provided some conceptual explanations for their theory, and they have a well-constructed presentation that's really easy for us to understand. And they have considered parameters such as the thickness of the coil, since it changes how heat is taken out of the surface area of the coil. And they have really clear illustrations. However, on the front, they have only quantitative only. And because they have no theory line, we can actually determine the velocity of the wind speed. And they have lack of data. And their time management is not best, and there's a photo of a setup. Now let's come to the opponents. They give a clear summary of the reporter's parameters, and they analyze the pros and cons. They give suggestions on how to improve the reporter's experiment, and they have ideas on how to they have good ideas on what parameters might affect the accuracy. The pros, they notice the pages and they brought up some critical questions. And for the cons, they don't have good time management. They spend too much time on topics with little importance, such as the relationship between thermal extension and resistivity. So, on to the discussions. The opponent stated that the surface area might change, and it should be considered, and the reporter stated that thermal expansion should be rather negligible. We think that it might be negligible to a naked eye, and we can prove without any experimental data. Okay, and what is the definition of their accuracy? And the reporter stated that the accuracy should be linearly of the graph. We don't agree with the reporter because the theory might not be conclusive enough. It doesn't involve enough parameters to actually accurately predict the wind speed of the speed. So a better way would be to compare the calculated wind speed with the actual wind speed. And the points missed. The missed out on the effect of room temperature and how it affects the accuracy of this way of measuring. And they have no theory in life. We can't actually have any actual accuracy analysis. And they don't have quantitative analysis. And not only this, they don't have enough experimental data to support their linear regression lines. And the cool-down process of the coil to be there might be some lag to detecting the cool-down process of the coil due to the conduction rate of the thermocouple, but they didn't investigate this. And they didn't investigate whether this supply is actually supplying constant voltage or current. And they didn't give the best parameters to minimize the interception. What's the best thickness?
Okay, thank you, Sam.
Thank you.
So, following the reporter, please make your 2 minutes concluding remark.
So first of all, I would like to thank both the opponent and the reviewer. I think that we had a very fruitful discussion and they asked some great questions. I'd just like to clarify a couple of things. First of all, there seems to be some confusion in terms of the lack of quantitative analysis and the lack of theory curves. However, if you go to one of our graphs, for example on slide 22, you can see that we do have linear fitted lines that we show on the graph. And as I mentioned, W is an experimental fitted parameter. So basically these lines are a theory curve because they demonstrate the linear relationship that we were describing in our theory with a certain parameter fitted to the experimental result. So So we did do a quantitative analysis here. We think that we have a clear definition of accuracy as the linearity of the points, the R-squared value, and the percentage error of the slope. And we do think that we considered relevant parameters to the cooling according to our theory. There also seemed to be some confusion on the part of the opponent in terms of our neglection of convection and radiation. However, in slide 10 of our PowerPoint, you can see that we have a very clear calculation for what the minimum ratio between the between the cooling rate due to convection and the cooling rate due to convection is. And this is about 200, so we can safely neglect this. And next slide, please. We can also safely neglect radiation because convection happens about 350 times more quickly or more. This is a minimum ratio that we're saying here. And also, there seems to be some confusion about our use of a thermocouple. Good questions that the reviewer asked. However, as I stated, we are measuring an equilibrium state here. So the rate of conduction of the thermocouple wouldn't be significant because we're assuming constant temperature of the coil when we're measuring it. And I think that's all the points I'm going to be able to address here, so that's the end of my remarks.
Okay, thank you. So I would like to ask all three presenters to stay on the stage and get ready to answer questions from the jury. So, yeah, please, first.
My first question to the board is that if you claim that there is no error bar so accurate, then how come your data is not fully on the pivot line? Can you explain that?
Okay, well, as I mentioned, there are some error factors that could be present in our data. For example, if you turn to slide 26, we can see the very slow wind velocities. We did notice a decrease in the wind speed between the front of the coil and the back of the coil, just due to the natural decay of the speed. We measured this at about 0.2 to 0.3 meters per second, and obviously with lower wind speeds, this is going to create a larger percentage error, so that's why we can see more error in the lower wind speeds towards the right of the graph. And in terms of the left of the graph, we also mentioned increased turbulence from the air supply as a potential cause of error. So there were some potential causes of error there.
I have a second question.
Oh, sorry. I think other juror to ask question first, then we come back to you. So any question? Yeah, please.
In the problem statement us, sentence says, what is the accuracy of this method of measuring the wind speed? The accuracy here is emphasize the methods. Well, let me say this. Isn't the best way to test the accuracy of the wind speed is you compare, you measure with a which is known. That should be the accuracy right here. Accuracy of the speed. You want to measure the speed. How accurate? Now your method can measure the speed, but also we can have a standard of the speed. Now you will come, suppose it is accurate, very accurate, then you will know how accurate your method is, right?
Right, I think that we have examined accuracy.
But I'm just trying to clarify your understanding. Now, I think you keep saying the accuracy. Linearity, inverse proportionality, it's all about your theory. It's not your accuracy or measuring speed. Is it different?
Well, because what we're trying to do here is we're trying to create a calibration curve, basically. We're trying to match up the temperature differences that we observe with the wind speed that we observe. And we think that when we create this curve, this line that's fitted to the data, this can be used for a given temperature difference to determine the wind speed.
I'm just saying, do you agree what I just said? That
yes.
So now, about to the opponent, I think you're asking what's the definition of accuracy? So what's your understanding?
I think they should define accuracy in the beginning, and the definition of accuracy should be able to explain whether you're...
So what's your thinking about the definition of the accuracy of this problem? I think that's the question jury asked.
I think it's the plus and minus, the weight velocity.
Okay, review.
I think it is the accuracy is the gap between the experiment and the theoretical value.
No. I think
That's okay.
Any other questions? If no, do you want to ask second?
Then I have a question to the opponent. And just now we have been mentioning that the summary expansion is a big factor. And can you explain how significant that would be and why and how that is going to affect the heat dissipation?
Do you mean whether the thermal expansion effect or not?
Yes.
Okay, I think so thermal expansion is going to change the resistance of the oil. And if
How big? How big it will affect?
It depends on the experimental data that's getting
Please
provided.
inspect.
Predict.
Yeah, please inspect. That's the question the jury asked.
I think it will be
1,000, 100, or 10 times, 100 times? About how much?
I think it will be maybe not less than 10 times.
10 times the actual value or anything?
Since that problem statement says that they need to have an accurate for measuring the heat speed, so I think they should consider more like some thermal expansion. Yes.
I think so. Yeah, please. Last question.
Just want to wonder, what's the time of the movement? To which you believe that?
I'm sorry.
You measure the different temperatures. We start with passing through. How long do you think
We didn't actually specifically measure that because we didn't consider that in our theory.
Please make some explanation. Jury need the number, so give him a number.
Minutes? Like on the order of minutes to reach equilibrium.
How much time you need to read this number, the temperature? It spends you some minutes or hour?
Well, on the order of minutes, I guess it varies depending on the experiment, but a relatively short amount of time.
So for minutes, something like that. Is it? So it takes some minutes to read every temperature, right? Okay, I think that's enough. So we move on to the scoring part. Okay, so as we already have all results for the jurors, so please raise your mark for the reporter. There are 6, 6, 8, 7, 5, 5, 7, 8, 8, 7.
Thank you.
And the score for the opponent. Okay. Please raise it. 9, 8, 7, 7, 5, 7, 8, 7, 6, 7.
Thank you.
And the score for the viewer. 9, 7, 8, 7, 7, 7, 6, 7, 6, 7. So we do have some distribution about the scorecard, and for some extraordinary score, please give, I would like to have some comments, and please start your comments from the partial grades. Okay, so they will know which part were subtracted more or less at the first glance. So for the reporter, we have 2, 5, and 3, 8. So how some comments from some 8. Yeah, please.
Okay, I read the form I gave to the reporter. 1, 5, 2.
So any comments?
Comments? I think he can explain his comments in a very clear way, and the way he treats the opponent and the reviewer are very friendly. And yeah, that's the way I like it.
Okay, so any comments?
Yes, I do appreciate the reporter's validation of the assumptions you made, theoretically, calculation, and but yes, the only drawback I can hear is that about the accuracy of the mistake, direct expression of that is exact here. Otherwise, probably will be even higher.
Okay, also we have 2, 5. So, you also got 8, please.
Yeah, I think I agree that the reporter did not really address the accuracy of the wind speed measurement, which is unfortunate. But I think in terms of the way that he was doing the science, and also especially I think why he ignored this part of the transfer, that part of the transfer, I think that is nice. So I gave him some good points.
Okay, so we got 2, 5. So I think
So I will first, as the chair asked, first the partial scores. So for the report, I gave 2.7, and for the discussion, I gave 1.5, and then answer to the question, I subtract 0.5. So the low grades on the report is that from my perspective, in the report, what you really explain is that why convection is important. Other than that, I don't get any idea why how temperature change from the convection. So actually what happens there. And then from your measurements, so we don't see, for example, if you change the wire thickness or not, but we don't. I can't get anything why when why it is more linear on this end. And also at the end, so the pocket has to check the accuracy. check about the method, this method for measuring wind speed, but we didn't do that, so therefore the report so I gave you only 2.7. And also during the discussion, so at the beginning, when your argument, your answer, you didn't give a very good I think. So the argument is that it's only with adjectives. So we did it this, we did it that, but finally you show some charts to prove your points. So that the discussion part, I subtract a little bit points from that. Okay, thank you.
Okay, then following in the opponent, we got the highest mark of 9 and lowest mark of 5. So how about give some comment about the 9?
I'm appreciating the opponent in a clear view about his points. I think that his points about accuracy is very important.
Okay, so about the 5?
Okay, so for the scores, so the question asked, I gave 1 point. For the presentation, I gave 1.7. And also the discussion, I gave 1.3. And also I subtract some points from the jury questions. That is about 0.8. And I think for the presentation, it's the same. Basically, the point I subtract is, again, the first stage. So for the summary of the reporter's point, so you didn't mention enough about the results and keys. So therefore, I suggest some points. But especially low grades on the discussion is that you spend too much time on the thermal expansion, and you didn't tell us anything why that is important and how important that is. As finally, the jury asked, and also some other questions. Okay. Also, for example, the question on the power supply power and so on. So for each point you ask, you didn't tell us why that is important during the discussion. That is a major drawback. So therefore, I subtract at least 1 point from the discussion.
Okay, for the reviewer, we got the 2.6, a lot of 7, 1.8, and 1.9. So I think we better to have any comments from the 9 or 8.
I'm appreciating the reporter to the best work about the viewer's job. we give. I gave the question asked for 1 and the review of a report for 2.5 and the review of opponent for 2. And plus the missed point up 1.
Okay. So I think that will be all. And some words I can add is that opponent is spend a lot of time mentioning about the thermal expansion. So whenever we mention something would be important, we will expect its effect will be big. And in physics, usually big is a relative term. So you need to know by what number it's big, by what number it's small. So better you have some idea about, for example, the diameter will expand by 3% or 10% or 10 times. So that will make it very different. So if the expansion is only something like 1 to the thousandth, usually we don't expect something. So that's why I think jurors ask why the expansion is important. Okay, so I think we can close this section and we will have some break time. So please come back after the break.
你有看直播哦？对啊。是啊。对啊，对啊，对啊。对啊。现在还有直播吗？打电话。
issue. So we can start the last round. And last round will be presented, the reporter will be Alexia, and the opponent will be Miracle, and the reviewer will be all-nighters. The problem to be presented will be number 7, beat dynamics. So we start from the preparation of the reporter in minutes. So reporter, you can start whenever you are ready.
So, dear chair, I think I'm ready for preparation. Excuse me, I'm ready for preparation. I'm ready.
Okay, since the reporters are ready, so we start the report for 12 minutes. Okay, please start.
Honorable judges and all the competitors, I'm the reporter from the team itself here, and the policy I'm going to represent number 7, B dynamics. And first is a problem statement. The circular hoop will take about a vertical diameter. A small wheel is allowed to roll in a hoop on the inside of the hoop. Investigate the relevant parameters affecting the dynamics of the bead. And my main focus is mainly about the motion of the bead and the effect in the different parameters and in different conditions. And this is my outline of my report. The first is introduction, which has includes the experimental setup and also has 2 key observations. And in my quantitative model, it has included about the equations of motion and also the simulation. And in the third part of my report is the experimental verification, which has equilibrium angle and also the oscillation frequency, which we will analyze it. And the fourth part, conclusion, which we will summarize our report. And first is our introduction. In our experimental setup, as the picture you can see that there is a motor which can control the rotational speed of the hoop. And there's also a circuit which is corresponding to the problem statement. And there's also an electromagnet and also a bead which sticks together. And we also use a camera to capture the movement of the bead, and which is fixed on the rotation of the turntable, which means when the turntable is rotating, it will turn with the turntable, so we can catch the every moment of the bead. And this is it works. As we press the button on the remote controller, the electromagnet will release the bead. So, which means we could release the bead whenever we want and wherever we want. And this is our observation. Our observation is just divided into 2 conditions. In the first conditions, it will oscillate at the bottom of the hoop, and finally stop at the bottom. And in other situations, it will oscillate on the hoop and gradually lead to a gradual decay, and finally it will stop at a certain angle. Then this is our qualitative explanation about the phenomenon. So as we see, it will finally stop at the position, which means an equilibrium position. And this position, the component of the number force will equal to the velocity, which means the situation is stable. But on the other hand, when the initial angle is lowered to the equilibrium position, found that the number force will increase, which means the component of the number force will be bigger than gravity, which means the bead will go up. But on the other hand, when the initial angle is bigger than the equilibrium angle, the component of the force will be smaller than the gravity, which it will start going down. So the phenomenon is basically based on these 2 situations, the cycle of these 2 situations, and it won't just reach the equilibrium position because of the inertia. Then there's our quantitative model. First, we should consider about here is the bead is rotating on the hoop, and the actual rotational radius is not the radius of the bead. So we should consider about the actual rotational radius, which is the L as our slide shows. So the actual displacement in the X will be like the 2 pi L multiplied by the numbers of turns.
Yeah, I'm going to start here about kinetic energy. The first we'll see about the section view of the bead, the groove. So as we can see this part, we can measure the contact points between these two grooves, and also we know the radius of the bead, so we can calculate the actual rotational radius it is. So in the kinetic energy, we can consider about the distance to the center of the mass of the bead will be r minus L. So the kinetic energy we should also consider about the horizontal one and the vertical one. And because the bead is rotating on the groove, so we should also consider about the rotational energy, which is very important. And third kinetic energy, we should consider about the rotational energy, and we consider the original point as the center of the cube in the three-dimensional motion. So the rotational energy will be like this. So the Lagrange equation, we found that is derived by the kinetic energy minus the potential energy. So after the partial differential and also the differential, we will get the equation of motion after calculating the Lagrange. And in this situation, we did not consider the air drag and the friction, which is the damping. So we will calculate the damping by using the torque to calculate the coefficient of the damping. And the torque of the bead, we will see that friction multiplied L equals I phi double dot. And in this situation, the phi dot will be the angular velocity as the bead is rotating on the groove. So the friction is derived by that. And this is the sum of the torques. In this situation, it didn't rotate. So there's also only the gravity torque, air drag torque, and also the friction torque. So after deriving these torques, and after the define of the different I prime like this, the final equation will be like this. And also, when the data is very small, it could be derived into this. And whereas after the differential equation, we will get a final equation will be like that. And where the true data is the coefficient of the damping. Then is the theory about the equilibrium position. Because when the bead starts oscillating, it will start at a certain position at the group. And after the equation, we found that when it stops moving, acceleration and the velocity will be zero. And we know that this part won't be zero, so the only solutions will be like this. So we can get the equation of the equilibrium position. So as we draw it to a graph, we found that there exists a critical rotational speed. So when the rotational speed is bigger than the critical rotational speed, we can get the equilibrium position bigger than zero. Then this is our simulation of the motion of the bead. As we look at the equation, which has included the damping in our equation, we'll put that in the code and do a simulation. So this is a simulation compared to our theory. We can find that it gradually decay because of damping and finally stop at a different position. And also that there is the deviation of the amplitude from the theory to the experiments. And this is because of the sliding motion that we have observed in our experiments. Because sometimes it's not pure rolling, sometimes it's sliding. So the amplitude might have a difference. And we have considered but not because it's too complicated to distinguish when it's rolling and when it's sliding. Is our analysis. First, remember is our initial angle of release. Our first initial angle of release is minus 10 degrees to minus 110 degrees. And this is our control variables. So by comparing the two different initial angles, which is minus 10 degrees and minus 50 degrees, we can know three important things. The first is that they have the same equilibrium angle, and compare the minus 50 degrees to the minus 10 degrees, there is an increased frequency. And the third, that it has a decreased amplitude. So after the first analysis is about the equilibrium position. So as just shows, it will finally stop at a certain position, which means equilibrium go. So after comparing different initial angles to the equilibrium position, we found that the equilibrium position will be the same. And also, by comparing the equation to the equilibrium position, we found there is no initial angle in the equation of the equilibrium position. So we say that the initial angle on the equilibrium position. Then this is our second analysis about the amplitude. We will analyze the second amplitude in the motion of the bead as the amplitude that we want to analyze it. And this is a graph of the comparing initial angles to the amplitude. And we found that when the initial angle is close to the equilibrium position, the amplitude will decrease. And this is our analysis about the oscillating time. And because we consider the amplitude at 0 when it's more than 1 degrees, which means the oscillating time will stop when the amplitude is 0. So after comparing the initial angles to the oscillating time, we found that when the initial angle is close to the equilibrium position, the oscillating time will decrease. And this is a whole analysis about frequency, and we use CFS for transform to analyze it. So by comparing two different initial angles, we found that there is two different frequencies about it. And by comparing the initial angles to the frequency equation, and also equation that is about approximately minus 63 degrees as the previous mentioned in the previous analysis, we found that the frequency will increase as the initial angle is close to the equilibrium position. Then this is our second experiment about the radius of the hoop, and our parameters are 17, 21, and 25 centimeters. And this is our control variables. And by comparing two different centimeters of the radius, we found that the 25 centimeters of radius has a higher equilibrium position. And this is our first analysis about the equilibrium position. So as we see in the equation of equilibrium position, there is a radius in the equation. So which the factors of the radius increase, the equilibrium position will increase, just as the graph shows. And this is a second aspect about rotational speed, critical rotational speed. So we know that critical rotational speed will be like this, and there's a factors of R. So we know that when the radius increases, the critical rotational speed will decrease. And this is our experiment about the rotational speed of the cube. And our parameters are different rotational speed, which is 80 to 100 rounds per minute. And this is our control variables. So by comparing the different rotational speed, we got there is a two important point, which is they have an increased equilibrium angle and frequency as the rotational speed increase. And after using more analysis to analyze the frequency when the amplitude is very small, we found that there is a different frequency when the rotational speed is different. And after comparing the different rotational speed, we found that when the rotational speed increases, the frequency will increase. And this is something that has about the equilibrium position. We found that when the rotational speed increases, the equilibrium position will increase, just as the equation shows. Here is a factor rotational speed squared in the equation. Then this is my conclusion. First is about motion, and we will oscillate on the groove, and we consider because of the component normal force and also the gravity. And because of the effect air traffic friction, the amplitude will decrease and it will start to decay and finally stop at a certain position. Then the summary about quantitative module. First is our critical velocity. We calculate the critical velocity by this. So which means the rotational speed should be bigger than the rotational speed in the equilibrium position will be bigger than 0. And we also use as simulation. We have an equation derived by the Lagrange and put them in the code and calculate the simulation and compare to the experiment. We can see it compares to our experiment very, very well. And then is the final point about summary about our experiment, which has the effect of different parameters, which has the rotational speed, and also the initial angle of the disc, and also the radius of the hoop. So as a graph sees, we can see that when the rotational speed starts to increase, the equilibrium position will increase. And we found that different radius has a different effect to our experiment. That the critical rotational speed will be decreased as the radius increase. And we also found that equal position will not change, only initial angle has a difference. So as we see the equation of the equilibrium position, that there is no initial angle will affect equilibrium position. So we might say that the initial angle won't affect the equilibrium position. And this is our references as we just mentioned in our theory. And thank you for listening.
Okay, thank you. So now is the time for opponent to ask your question. Your time is 2 minutes.
So here's some two questions. First, can you go to your page where you're talking about your theory?
Okay, please turn to the page page 10.
Okay, so can I ask you that in what reference frame are you using in this theory?
Excuse me?
In what frame of reference are you using in this theory? What's frame of reference?
Reference.
Is it in a inertial frame of reference, or is it in a rotational frame of reference?
I'm not sure about names.
What coordinate are you using? Is it fixed at a point, or it is turning along with the loop?
Do you mean the torque part? Torque?
I think the coordinate system. What are you using in?
We set the original point as the center of the cube, so we're
okay, so it is rotating with the center of the cube.
Yes.
Okay, next, have you ever considered adding a potential term about the efficient potential of the centrifugal force. Okay. And next, in your theory, you have considered the friction force as is the friction force a static friction or a kinetic friction?
It might be a static friction or kinetic friction, depends on if it's a rolling situation. When it's static situation, it might be a friction, but if it's a pure rolling, it might be a static friction.
Do you check if it's a pure rolling or is a slipping roll?
You might have a sliding motion or so it has a rolling situation. Depends on, we have to observe how it rolls on the groove.
Okay, next, can you ensure that the rotational axis is along the vertical axis and there's no some aligned problems?
What problems?
Like the rotational axis is straight in the vertical axis, and can you ensure that it does not like have a angle?
No, you're not sure that.
Okay.
Okay, now we move on to the preparation of the component. Okay, so I think your opponents are ready. Opponent is ready. So please start your presentation for up to 4 minutes.
Okay. So morning, and I'm the opponent from Typt opposing Harvard number 7 fluid dynamics. So first, let us first take an overview of the report. About the phenomenon, the report shows that there is an oscillation and decay between the equilibrium point. And next, the reporter shows that the feed state is stable at a certain height. And about the feed, first, the report analyzes the equilibrium point and has a consideration of the translational and also the rotational energy, to consider the both as a rigid body. And next, as my question, the reporter says that in the theory it is in a rotational frame, and he considered the gravitational potential energy, but from the point of view from the opponent, in a reference frame in rotational, he should also consider an efficient centrifugal force. And that's about the setup. The reporter uses a electromagnetic release and take a camera to make sure that the film is rotating along with the hoop. And finally, with the experimental data, the reporter shows some comparison between theory and experiment, but somehow it has an inconsistency between the theory and experiment, as we can see that they are not match perfect. So here are the pros and cons. First, Porter has a very dynamic diagram showing how he calculated his theory and how the experiment is conducted. And next is some clear graphs that explain the phenomenon. And next Porter has a good time management, and finally, we also consider it as a structured report. However, here are the cons. First, as I said, there are some inconsistency with the experiment and the theory, so we consider it as a understated theory because it does not provide a thorough explanation on the main part that the opponent thinks is the most important, which is the friction and the drag forces. And next, does not have an intuitive explanation about how about what is the physical meaning of the equations of motion. And next, some phenomena is not thoroughly explained in it. Some phenomena is not thoroughly explained, and there are some informative graphical explanation, as we can see, with the deviation between the theory and experiment. And finally, some parameters that the opponent think is very important is not changed. So here are points to discuss. First, my main focus is on the theory and how it applies to the experimental data. And first, so we want to discuss the forces, the friction force, the air drag, and some turbulence when the hoop is rotating, and the direction of and magnitude of the friction. Next, we want to discuss the equilibrium position and what the tilt angle would like to affect on the phenomenon. Next, about the dynamics, we would like to discuss the how to start the motion and how to interrupt the stabilization at the lowest point, and some discussion about what will happen if the reporter acts to a hoop. And next, I would like to discuss the experiment and how to control the angular velocity and the total moments of inertia at the center of mass. And next, about the rolling beam, we're going to discuss what is the effect about the radius and mass, and if it's a point mass of the rigid body. And finally, some experimental details. We want to have a discussion on the data capture about the optical aberration of the camera and some distortion. And I would like to start now.
Okay, please start the discussion.
Okay, so first off, about the theory, can you tell me again how do you consider the friction?
I consider friction depends on when it's rolling or sliding, but it's too complicated to distinguish when it is sliding or rolling, so we can see whether that is the
okay, so can you tell me how do you define the definition of, the direction of the friction? Can you draw it on the back whiteboard?
Okay, so consider this as a groove, and this is a B-rotating groove, so when it's rotated about this way, and the friction will be about this way, so we should consider about the static friction of it.
So you're considering that is also static friction, is that correct?
In our assumption is that.
Well, but in my point of view, you're considering as a static friction. In this case, I can be sure that if it's static friction, the contact point of the beam and the hoop is at the minimum point. But in your experiment, I'm assuming that the contact point is here, correct?
That's right.
So it's rolling. I'm not really sure that it is static friction because it's obviously that this part will move, and it's not the case in this part where this part may not move.
And it's that, so we have a group of this, and we have to read on this, and we have to talk about the actual rotational radius about the L, and to the contact point that we have to consider about it. So this point, the contact point might be this part, and it will have a static friction to the group, and also sometimes it has a kinetic friction.
Can you show me what is on which point does the friction force exert?
Please turn to page 10. Also, we can see the section view of the grooves and also the beats on it, so which means this is not a point.
Okay, so if it's a static friction, you're saying that this does not move. Is that correct?
Do not move at all.
If it's a static friction, the contact points must not move.
When it's rolling? Or?
Yeah, that's in your consideration. This point does not move.
Really good.
So from the opponent's point of view, if you want to consider a pure roll and a center friction, the only problem point that may not move is this point. But in my point of view, you might consider this as a kinetic friction. And do you think that the difference of kinetic friction and a center friction?
Well, there's no point of here and how do you consider it?
Yes. So I think that if there's an experiment that can consider the center friction,
sorry, either experiments or...
No, I'm saying that in your experiment, yes. I think you can only consider a kinetic friction because the contact point is not here. That's what I'm saying. Do you think that the difference between a kinetic friction and a static friction will affect your the accuracy of your theory? Can you show me the page where...
Oh, sorry, can you send to page 15?
Yes, please.
Okay, so you can see that there's many about the ambiguous deviations in the theory that because of signing it might not move as far as if you're rolling, so that might have an ambiguous deviations in that.
Okay, so can you quickly tell me what is the main reason that there is some ambiguous deviation?
Deviation of what? There's so many about that. I mentioned about the ambiguous deviations about that because there's a difference between the pure rolling and the sliding, but in the actual situations, the pure rolling and the sliding situation both happen in our experiments.
Okay, so can you define at which point there is pure rolling happening? And
also, excuse me, I don't know what you're meaning. So in experiment, we use the observation video. We could use when our B is rolling on it, and we'll use a red mark to mark it. So as we can see that as it is rolling, we could calculate the radius of it has a rotation. And also consider about that this is the theta and this is the radius. We know that if radius theta will equals the if this is rotational radius will equals the L phi, which is the radius they have moved.
Okay, so that's your confirmation that it's a pure rolling. Yes. Okay, so if you take this consideration back into your theory, do you think that changing the frictions from static friction to kinetic friction can help improve your theory?
Yes, I think so, but it's very difficult to distinguish if it is rolling and to distinguish because the kinetic friction and static friction might happen in different situations.
Okay, next I want to have you consider how to consider the drag force. What is the form of the drag force?
The drag force it has includes the air drag and also the friction.
I'm saying that about the air drag. Yes.
And please turn to page 5. So as you see that there is the air drag force which is minus B and
you're considering that is proportional to the square of the velocity. You're considering the air drag is proportional to the square of the velocity. Do you have any verification of this power? Because as my knowledge of a drag force, when the speed increases, the drag force the proportionality can change from power to 1 to this continuous change from the first power to the second power. No, I'm saying that have you ever had a verification on this second power of the proportionality?
No, but we use it. This is a group, and we put a beat on it, and in a small angle because this is how the equation will be applying, and we found that it will oscillate at the bottom of the starting position. So we use this to consider about all air drag integration.
Well, do you notice that as the speed of the beat goes up, the form of the air drag force will differ. But in this case, I'm considering that you're using the same air drag at the same time, all the time. Is that correct?
In our assumption, it is.
Okay. And next, can you show me that in your graph there's a point that the equilibrium position is slightly different with your theoretical equilibrium position?
You mean the equilibrium position and which charge? Equilibrium position to which values?
So the point you're comparing your experimental equilibrium position and your theoretical equilibrium position.
Sorry, page 19. Do we describe?
Yes. Have you any explanations on what is these kind of deviations?
The deviations might slightly initial angles. We might have 1 degree or 2 degrees, because this is our electromagnet and might have little deviations where we face the beyond, so they might have little deviations. Sometimes our rotational speed is
sometimes it has a little deviation because of apparatus. Do you think that the direction of the friction you're considering wrong that makes this really somehow paradoxical to something? One thing is that when it's stable and equilibrium, we can all agree that it is a center friction, correct? Right. Yes. Center friction can be from two directions, this direction or this direction. Have you ever had like determining which direction the center friction is?
I think it's yours more than you mentioned.
Is it this one?
I guess no question.
Okay, so we don't know that the direction of the center friction is towards the negative direction where the beam tends to go.
Sorry,
in its condition where it will, which part will it roll? Sorry? In its condition, how the beam rolls to which direction? I think that, can you tell me again how, in your theory, which in the equilibrium, where do you consider the direction of the friction?
No, so when it's rolling this hard, rolling this way, there's center friction.
Well, I'm saying that it is it's stable at the equilibrium.
It's stable at the equilibrium?
Yes, but where
it's stable? So you mean when it's stable?
Yeah, in this way. Just theta is the equilibrium.
It might both consider. Both directions might be considered.
Not like which direction? This direction or this direction?
Might be this one. No. Number one.
This one. So you're saying
number one.
This one.
Might be.
Can you like how you explain why it is this one?
I think we can distinguish that because when the beam is not moving, and because sometimes the rotational speed might have a deviation that it will might be degrees, so sometimes the component of the force might be a little smaller in gravity, so sometimes it might have a friction.
I agree to you that I believe that this friction is also in this direction, but another explanation. So when the hook is rotating, the beam tends to go somewhere. Right?
Yes.
So if it's in a stable plane, I think it's fixed because of the friction. So the beam is because of the manual energy from the stable. Yeah. So I believe that the main point of the why the friction is in this direction. Okay. So moving next, do you ever consider when your beam is rolling, it is changing the center of mass of your group, and it's changing the moment of inertia of the group, and that will affect your rotational angular velocity.
Meaning of changing the center of
So your motor is rotating total system, correct? Yes. When a beam is here and a beam is here, I think that the moment of inertia will change. And do you think that it might affect your experimental angular velocity?
I don't think so.
You don't think so?
Yes.
So you think that this is considered too small?
So I think the time is up.
Okay.
Thank you.
So to conclude our discussion, first we have the discussion about the forces such as the friction force and the air drag turbulence. And first we have some discussion on friction, whether it is a purely based a center friction or whether it is a slipping which it causes a kinetic friction. So when Porter says that in his experiments they can verify if it's a center friction, if it's a purely or not, but they not add it into their theory, and so in their theory their consideration is that it's all center friction, and I think that is quite questionable, because I think that if you add a kinetic friction in your theory, it might improve the theory line and the accuracy of the theory. And next we have under the direction of and the magnitude of the friction, and we have an agreement on the direction of the friction and the stable point end, but we have different explanation, and believe that the explanation is that the force will tend to going up that makes the direction goes down.
So I would like to ask a reporter and opponent to stay on the stage. Opponent.
Alright, so
sorry. Wait for them to stay on the stage. So please start your question.
Alright, so first question to the reporter. Does the reporter have a graph of the equilibrium angle versus angular velocity that describes the complete effect of backwardation?
You mean angular velocity of the rotational speed of the group?
Yes.
Okay, wait a minute. Please turn to page 28.
Okay, cool.
Next page, please.
Okay, cool. Thank you. So for the opponent, what is the force that causes the beam to rise?
Sorry?
what's the force that caused the beat to rise?
To rise. It's the centrifugal force.
Okay, same question for the reporter. What is the force that causes the beat to rise?
Centrifugal force.
Okay, and then another question for both of you. What makes the beat go left and right? Assuming that I place the beat at the bottom and you increase the angular velocity.
Okay, so why the beat has an oscillation about the equilibrium point is because the first exceeds has a higher velocity and causes what causes it to decay is about the direction.
Thank you.
Can you repeat again, please?
What causes the beat to go left or right? Assuming that I place the beat at the very bottom.
Right, the 200 value initial angle, so it should just stay at the bottom and use azimuth.
Okay, thank you. And then another question for the reporter. What happens when the angular velocity approaches infinity? And also, when it approaches infinity, is the movement of the beat stable at the top or unstable?
At the top, because our equations will show that equilibrium position will over the 90 degrees, and if it's infinity, it will be close to 90 degrees.
Okay, thank you. What about
I agree with the reporter.
Okay, next question. For the reporter, when you change your parameters, did you change the parameters one by one or all together?
Excuse me?
When you change the parameters, did you change multiple parameters all together or one by one?
No, just one by one.
Okay, next question. Also, for the reporter, how do you think sliding friction do you think sliding friction exists when the ball rolls?
Sliding friction, you mean sliding friction?
Yes.
Yeah. We have to consider that we're going to put it in here because it's complicated to put it into both this static and kinetic friction.
Okay, thank you. What about the opponent?
Well, I think that the kinetic friction always exists.
Okay, and last question. For the opponent, how do you think the mass would affect the phenomenon? Mass of the beam.
Okay, so if the mass of the beam is considerably large, and when the beam is rolling, it will actually affect the inertial and moment of inertia of the total system, and which will affect the angular velocity.
That's it.
Okay, I think time is up. So now is the time for reviewer to prepare. Okay, since time's up, please start your presentation.
Hi, I'm Daniel from the All-Nighters, and I'll be reviewing number 7, beat dynamics. Alright, so this is the problem statement, and these are my main focuses. So the first one, what are the relevant parameters? Number 2, how can we determine the equilibrium angle, which is the critical angular velocity? Number 3, how can we explain the oscillatory behavior? And number 4, most importantly, how can we investigate the dynamics of the beat? Alright, so here is the reporter's performance. This is the phenomenon. With different angular velocities, the beat will move to different equilibrium points. This is the reporter's theory. He investigated the rigid model, the rigid body model, he had a clear phenomenon footage, he had a pretty good quantitative theory. The reporter also caught up with RCM. He also examined the oscillatory behavior of the beat. And lastly, he also discussed the boundary conditions. However, for the cons, the reporter didn't probably explain the rate of change in the equilibrium angle. And then he also did not analyze the beat at the bottom of the hoop, which is percentage of the maximum angular velocity. And also, the reporter, the graph of the angular velocity versus the equilibrium angular position graph, the scope should be larger, which I'll discuss later. And there was also a lack of parameters such as the material, the mass, and the radius of the beat. Alright, so the opponent's performance. Summary of the parameters, and then also the reporter considered the oscillation and the decay at the equilibrium point. The pros were that there was a good overview of the report presentation. He considered the lack of parameters the reporter had, and also there was a good analysis of reporter theory. And here are the cons. I thought the opponent provided a good explanation for how changing a relevant parameter may affect the phenomenon. He also challenged the report's inclusion of friction, but provided no way of accounting it in the theory, and also pointed out possibility of slipping to the beat, but in no way of determining the slipping. Alright, so this is the first discussion topic. Can you tell me the direction of friction? The reporter said that it is opposite the beat's movement, and I agree with the reporter that the friction opposes the movement of the beat in the plane of the beat. Alright, next, what is the reason that there are amplitude of deviations? The reporter says that the rolling and sliding friction. So I agree the rolling and sliding friction cause deviations in the oscillations caused by differences in the beat material. Alright, next up, do you consider drag force? The reporter assumed the same air drag for all velocities. I believe that this is false. The air drag increases as the velocity increases. Next, is the beat stable at the equilibrium point? The reporter said yes. I believe that the beat oscillates until it reaches the equilibrium point based on the angular velocity. Alright, so here I think are the points missed. So I think that the reporter and his report could consider a few more parameters, such as the mass of the beat. I believe the mass of the beat would change both the oscillation time and also the equilibrium position as the mass changes the gravitational force, and also for example, increasing the mass would cause the beat to oscillate more. And both the opponent and the reporter did not address how the slipping of the ball in the loop might affect the accuracy of the velocity. And also lastly, they both missed a theoretical explanation for the rate of change in the equilibrium angle when the loop is spun at different angular velocities. And also, I would like to suggest that the reporter provide a larger scale graph of the effect of the bifurcation. So this is the critical angular velocity, and over here is what would happen if it went to the right.
Sorry, the time is up.
Alright, thank you.
So following will be the time for the reporter to make the concluding remark for 2 minutes.
So I'm going to do a concluding remark. At first, a summary about the positive explanation, which has the beat is something, the movement depends on the number of force, and also the gravity, the component of the number of force. And also, if it will decay, but it decays and might establish a certain position, it's because of the air drag and friction, which is the same thing. And also, this is a quantitative model, which we have considered about the critical rotational speed that it will reaches. And also, we could simulate that in our code and do a numerical solution. And look at it has fit our experiment very, very well. And this is a summary about our experiment. So we have the different effect of different parameters that rotational speed, initial angle of release, and also radius of the loop. So we found that the different parameters in which the rotational speed will affect the equilibrium position as described very clearly. And also we found that the initial angle will affect the equilibrium position. Then to my remark, and we are sure that the cube rotating the vertical axis after multiple times we check it. And also we assume that the motion in our experiment is at a pure rolling, so it will disconnect friction. And also we believe that a sliding situation will happen, but the theoretical model still fits our experimental rate result in predicted parts. And also we believe that the deviation might happen due to the sliding motion that we have considered and calculated. And in the form of drag force, we have been considered the air drag and so the friction. There are many reasons for the damping motion because that in our cost torque, and we have calculated in our torque, we calculated the coefficient of the damping. And the control panel is used to experiment. Therefore, no that the moment of inertia will be affecting the angular velocity would be the same. And also the beat would rise to 90 degrees when the angular velocity is close to infinity due to the equation of motor position, and also because the supporting of the groove will allow it to stay over the 90 degrees. And also we didn't put our mass as our experimental parameters because the mass will also change the moment of inertia, which will in order to change the motion of the beat.
Okay, thank you, sir. So, finally, I would like to ask all three presenters to stay on the stage. So, jurors, any questions? Jurors? Any questions? Yeah, please.
Question for reporter. Okay. In your summary, you say for infinite angular velocity, then the equilibrium angle will be 90 degrees.
Okay.
But that seems to be not realistic, right? If you consider this a sliding or...
sorry, I didn't read my... equilibrium position will be that because in a constant rotational speed. And because in a constant rotational speed, the centrifugal force will go more upward when the angle is bigger than 90 degrees. There is no support force of the groove.
You have to take into account that the infinite speed, the ball will not always sliding. Rolling, it will be sliding, right?
You mean a sliding and rolling situation?
So the friction might be different.
Yes, right.
Any further question? Yeah, please.
The question for what's the importance of distribution guidance
What is the key importance to distinguish between sliding and rolling?
Because in sliding situation, it will move that part because of the kinetic friction. But if you're rolling, because of static friction, the amplitude will be bigger than the sliding situation.
Okay, so there are 2 points. First, the difference from pure rolling and slipping is the friction will change. And the second point is that the difference is that you cannot just calculate if it is not pure rolling, you cannot just calculate the velocity regarding of the angular velocity. You have to add another linear velocity.
Hello? I feel like the key point of the rolling and sliding friction is that both will sort of cause the beat to oscillate and to eventually reach the equilibrium position.
Okay, yeah, please.
Please, we all have. What will happen if the beat is much smaller than the width of the groove?
Sorry, you mean the beat radius is more than it can roll on the groove? You mean the beat is smaller than the groove strength? Because our groove is 2 different strengths of it, so it is more than that. You can have a contact point I mentioned like that. Just like the 2. In our experiment, we use a 2 groove and we put a beat.
What's the difference?
What's the difference? So if it is more than that, it will start collision because the beat is under a groove this part, so it will make collision to the different side of the groove.
Okay, so if the size of the beat is much smaller than the groove, we have to add another force, which is Coriolis force, and that force has a contribution to the direction in the width of the groove.
I think that if the radius is much smaller, of the beat is much smaller, then the distance between the beat and the center of the circle will be larger, so that will increase the centrifugal force. And also, I feel like if the beat is very, very small, you can possibly use a point particle theory instead of a rigid body theory that the reporter proposed to maybe analyze that.
Okay, so any further? Yeah, please.
I can see the reporter has explained why you need to use the mass as the parameter, but the reviewer of the proponent seems to suggest mass can be a good parameter. what's your opinion? What are your two opinions about the reporters' arguments? That's like a social opinion. You said you didn't choose math because it affects the initial moment. Yeah, and I wonder how the review has anything about this.
Is the judge's question about the mass as a parameter?
Yeah, do you think it's a good parameter or not necessarily?
Well, I don't know about the moment of inertia. I don't think that directly correlates with the mass and speed, but I feel like the mass would first of all increase the gravitational force on the bead, which would, if the mass is increased, then it would lower the equilibrium position. But also, if the mass was, for example, increased, it would also increase the oscillation time, as it takes longer to oscillate and reach the equilibrium position.
Yes, I agree with the reviewer that changing the mass not only changes its moment of inertia, but because the friction and the drag forces are not independent of mass, it changes when mass increases, it changes the duration when it finally stays at equilibrium position.
Okay, so I think we can move to the scoring part. I see all the scores were made. So please raise the points for the reporter. There are 7, 8, 8, 7, 7, 8, 8, 8, 8, 6.
Juries.
And score for the opponent. 7, 7, 7, 8, 6, 7, 7, 6, 7, 8. And the score for the viewer. 7, 8, 8, 6, 7, 7, 7, 7, 7, 8. Okay, so I think for all three teams, the scores given are quite consistent. So I would just ask any comments to be given, or no? It's okay. Yeah, please.
In the beginning, opponent asked the reporter what frame of reference you were using. Well, since he's using Lagrangian formalism with R radius and theta and phi, and then he wrote the Lagrangian. So that's it. You don't ask what frame is he using. There's no point, because if you write out the Lagrangian, then everything is by Euler Lagrangian equations. But if you use Newtonian formalism, then you have to be careful. You have to distinguish inertial frame from non-inertial frame. And that's the one advantage of using Lagrangian formalism. It's not answer. You know, I know what's in your mind. You said about Coriolis force. In Lagrangian formalism, you don't have that. Because once you roll the T loads the potential energy, then that's it. But in Newtonian mechanics, if you use rotating frame, then you have the Coriolis force, you have the centrifugal force, which arises because of its non-inertial frame, but not in Lagrangian formalism. And I emphasize it. That's the advantage. Although most of you just keep using Lagrangian formalism without realizing that that's the advantage. Otherwise, Newtonian mechanics is adequate to answer all questions. Sometimes even in more detail, in more physical insight. So that's my comment, because I think Lagrangians used abusively in almost reports. And so you have at least understand this advantage of the formalism.
So I think professors, what he means is that whenever you write down the Lagrangian, actually you already automatically you fix your discussion into corresponding coordinate, and everything will come out automatically by mathematics. Okay, that's what it means. And I think maybe your question has different meanings, so I think that's something that can be discussed. Something like, do they know they are in the rotating coordinate or not? Something like that. I think that's the difference. Okay. Yeah, please.
Make a quick comment, because I think scope 6 was important. Yeah, because I think you mentioned that you cannot distinguish the rolling or sliding in the experiment. Yeah, but I think in experiment it should be possible. You can make some simple marking and observing. You should be able to tell. Yeah, and because that's also important, because in model you talk about friction, how we give the ball. So I think that's whether it's rolling or sliding, it's actually an important issue for your model. Yeah, that's just one comment again.
Okay, so I think that I personally have some comment about the reporter. Actually, the problem said a small beat. But when I look at your picture and your video, actually your beat is not small. No. Okay. I didn't complain about that anyway. I didn't give you any points. Okay, so because I'm enjoying the discussion about the problem decision discussion. So during the discussion, actually they discuss about the size of the bead and also the dimension of the bead. I mean dimension also means the mass. Okay. So actually, but at the beginning we expect more complicated behavior of the bead, something like the three-dimensional motion. Okay. So, but anyway, you already done a very good job, so that's why you get quite high scores.
Thank you.
And okay, so right now we already finished all 3 rounds and all the points are even. So I would like to close the final fight section, and thanks all 3 teams, and also thanks all the jurors for a very long time focusing and give points and comments. And thanks all. And we will have a banquet after. Then we will come back before 3 for the closing ceremony. Yeah. Okay, thank you. Thank you, everybody.